All right, let's dive right in. Today, we're taking a look at something that honestly sounds like pure science fiction, but it's actively unfolding right now in underground laboratories all around the world. We're talking about quantum computing. Now, usually, trying to understand this topic means hitting a massive brick wall of dense, linear algebra and super intimidating math. But today, we're going to treat this like the ultimate magic trick. We're stripping away all those equations to reveal exactly how the illusion actually works. By the end of this explainer, you're going to understand the physical reality that makes quantum computers so unbelievably powerful and why they are literally poised to completely change human history.
Okay, just take a second and look at this number. 2 to the power of 300. Wait, let that really sink in. In our normal, classical computing world, adding more bits just gives you a little bit more processing power. But in the quantum world, the power scales exponentially. If you have just 300 quantum bits, or qubits, in a fully entangled state, the amount of classical information they can hold at one single moment is equivalent to 2 to the power of 300. Guys, that is more than the number of atoms in the entire observable universe. And all of that potential is contained in just 300 qubits.
And this is exactly why the world's top scientists are practically obsessed right now. Back in October 2019, Google announced a massive, historic milestone. They called it quantum supremacy, using their Sycamore processor. They essentially faced this incredibly complex mathematical problem. Now, the world's most powerful classical supercomputer at the time, a massive humming beast of a machine, was estimated to need around 10,000 years to solve it. Google's quantum processor? It solved the whole thing in 200 seconds. I mean, it didn't just break records, it completely broke our understanding of what a machine could even do. But how? How does it actually pull off this reality-bending speed?
Well, to figure out the trick, we've got to look at the basic building blocks. Pretty much every device you own, your phone, your laptop, even those massive supercomputers simulating global weather, they all run on classical bits. Think of a classical bit like a basic light switch. It's always strictly either a 0 or a 1, off or on. Simple, right? But a quantum bit, or a qubit, behaves completely differently. Instead of a switch, I want you to picture a qubit as a coin that's actively spinning in the air. While it's spinning, it isn't just heads and it isn't just tails. It's this dynamic, fluid mixture of both 0 and 1 at the exact same time.
But honestly, that spinning coin is just the beginning of the illusion. To make a quantum computer actually work, physicists rely on 3 mind-bending rules of quantum mechanics. You can think of these as the 3 pillars, or even the 3 spells of quantum magic: superposition, entanglement, and interference. Let's break these down real quick, because these 3 things are the true engines driving the entire machine.
Let's start with Pillar 1, superposition. In our everyday world, things are pretty definite. A car is parked or it's moving. But at the subatomic, quantum level, things can exist in a state of multiple possibilities. Remember our spinning coin? A qubit in superposition actively holds both a 0 and a 1 state simultaneously. It's only when we force it to stop, like when we measure it or observe it, that it collapses into a definite 0 or a definite 1. And that word collapse is absolutely crucial here. It shows just how incredibly fragile this state really is. But as long as it's perfectly isolated and spinning, it's holding all those possibilities at once.
Okay, moving right along to Pillar 2, and this is where things get genuinely spooky. Entanglement. Imagine you have 2 of those spinning coins, and you entangle them. Suddenly, they share this invisible, instantaneous connection. Albert Einstein famously called this spooky action at a distance because, honestly, it completely defies standard physics. If you force one coin to land on heads, the other instantly reacts no matter how far apart they are in the universe. So in a quantum computer, entangling qubits creates a massive mathematical correlation. You don't need physical wires connecting every single piece of data. They're just bound together, which allows the system's processing power to literally double with every single qubit you add.
So the catch here is we have all these spinning, interconnected qubits holding every possible answer to a problem. But if we just look at them and measure them randomly, we're going to get a random, totally useless answer. And that is exactly where Pillar 3 comes in: interference. Imagine the qubits are performing this chaotic, highly complex group dance. Interference is essentially the music we play to guide that dance. Using wave mechanics, scientists create what's called constructive interference to amplify the probability of the correct answer, and destructive interference to just cancel out all the wrong ones. So when the music stops and those coins finally land, the system is highly biased to give you the exact right answer.
Now, to really lock this whole concept in, I want you to picture a maze. Just imagine the most massive, impossibly complex maze you have ever seen in your life, with millions of branching paths and frustrating dead ends. And your one goal is to find the single correct path to the center.
A classical computer solves this maze exactly how you or I would. It picks a path, runs down it, hits a dead end, backs all the way up, and tries the next one. Sure, it does this incredibly fast, but it still has to check them sequentially, one by one. A quantum computer doesn't do that at all. Because of superposition and entanglement, a quantum machine acts like a massive flood of water just unleashed over the entire maze. It doesn't check paths sequentially. It flows down every single path at the exact same instant. It's using computational parallelism to explore the whole problem space at once.
Now, hearing about all this insane processing power, you might immediately think of the biggest tech trend going on today, artificial intelligence. Training massive AI models requires just an incomprehensible amount of math. Take an open AI model like Meta's Llama 3.1, for example. It has 405 billion parameters. If you tried to train that model on a single standard classical GPU, it would take you 4,486 years. We only get around this today by stringing tens of thousands of GPUs together in massive data centers. So logically, shouldn't a quantum computer just crush this AI training in seconds?
Well, here's why it's actually not that simple. AI models operate on deterministic data. We're talking strict, rigid grids of zeros and ones, multiplying massive matrices of definite numbers. Classical GPUs are absolutely incredible at this, but quantum processing units, or QPUs, they are probabilistic. Their entire advantage comes from being fluid and holding multiple states. If you try to force a quantum machine to act like a rigid calculator just to do standard binary math for an AI, you completely lose the magic. It would be like buying a multi-million-dollar Formula One car just to push it down the aisle at your local grocery store. It's just not what it's built for.
And that brings us to the harsh reality of this magic trick. It is incredibly, incredibly fragile. There's this phenomenon known as decoherence. You see, qubits are notoriously delicate. Actually, some researchers compare them to that touch-me-not plant, the one that instantly recoils and folds up the second you brush against its leaves. The slightest bit of heat, a tiny physical vibration, or literally even just the act of observing them causes that superposition to collapse. The magic vanishes instantly, and your whole system crashes into a totally useless state.
Because of this extreme delicacy, quantum computers look absolutely nothing like the sleek laptops we carry around. They look like these massive, complex, steampunk golden chandeliers. And those chandeliers are essentially just giant, superpowered refrigerators. To keep the qubits stable enough to perform even a basic calculation, the processor has to be kept at a fraction of a degree above absolute zero. That is, minus 273 degrees Celsius. That's literally colder than deep space. So no, a quantum computer will definitely not be sitting on your desk replacing your PC to help you check emails or watch videos anytime soon.
So, what is all this actually for then? Ultimately, quantum computing isn't about running our old software a little bit faster. It's about unlocking entirely new realms of science. We're talking about designing personalized, life-saving drugs at the molecular level, discovering new materials for batteries that literally never degrade, unlocking the fundamental physics of the universe that our current computers just cannot process. The question isn't whether quantum computers will replace your laptop. The real question is, what impossible mysteries will humanity finally solve when we can hold the power of the universe inside a freezing golden chandelier? Thank you for joining me on this explainer today, and remember to keep questioning the impossible.